What's up, everybody? Today we're going to talk about something called great word problem, and this problem is usually shown to be the first example as a motivating example to teach something called reinforcement learning. I mean, this is like the first step. This is like the first step of 1,000 miles, right? And however, since Bellman, okay, I'm going to talk about each term individually, right, step by step, and so don't worry about it. And since Bellman equation is used in solving this problem, right, and since Bellman equation is related to control, I decided to focus on this problem. And also additionally, the reason why I focus on this problem, it took me a lot of times to comprehend this problem and comprehend also the algorithm, the value iteration algorithm. The name is called. I'm going to, by the way, let me write each one of them one by one, right? First of all, Bellman equation. Okay, one. After that, the name of the Bellman equation is the equation, and in the, I don't know how to say that. I mean, the similar version that in controller we are familiar with is Hamilton, Jacobi, Bellman, right? Okay. If you are as a researcher in control, this is the name that you are familiar with, probably. And there is a connection between those two equations, right? And the name of the problem, that the motivating example, is called great word. And there are a lot of videos about this. However, it took, I mean, every video I noticed, they explain everything perfect except some minor details, right? And that's really frustrating. That was really frustrating for me when I was trying to solve and understand the algorithm, value iteration algorithm. Yeah, let me write that. Value iteration algorithm. And this is the algorithm that we are going to implement in that problem, for that problem, and by solving that. And I am now focused on my notes. Okay, this is the Bellman equation, right? And let me read that. And this is the grid problem. Okay, we are going to focus. It doesn't matter if you don't know anything about this. Just step by step, I am going to explain that. I would like somebody to explain that to me, like the same way somebody. Let me say that again. I am going to explain the same way that I would like somebody to explain that to me, right? And any material, actually, right? So don't worry about it. And okay, this is great word. All right, there are, this is 3 by 4 3 by 4 matrix, right, or grid, right? And there are, each one of them are called states. Of course, there is a difference between the state space, state space that we are familiar with. However, the state in that problem, there's a difference that I am going to explain that as we move along, right? Okay. This is wrong anyway. It's 12, minor typo. And okay, this is a wall, right? And this is, these two states are terminal states. Write that down. Terminal states, right? And that's really annoying. Anyway, the reward of getting there or being there is +1 reward, right? And I mean, maybe penalty, you can say that. And reward of being in state 8 is -1. Alright, so far so good. And also, they also say that reward of staying alive is 0. Okay, you don't get to get a reward just for staying alive. And these two states are terminal states, meaning if you, let's say you are here and you move to that location and the game is over, right? And because you arrive at a terminal station, and there are actually two you can think of it that way, two terminal states: good terminal states and bad terminal states. Like, let's say you are playing a game, right? There are two ways that you can terminate the game, meaning first you can just die in the game, right? And as everybody knows, if you die in the game, you also die in the real world. And anyway, if you die, the game over, right? The game finishes. And however, if you, let's say, complete the achievement, okay, the game terminates again, right? Alright, there are two ways that one can terminate a game. One by getting the positive reward, and one by getting the negative reward. Let's say you are playing Mario and dying in the game is getting, you can consider it that way, getting negative reward, getting some penalty. Alright, and it completing the objective is getting the positive reward. Okay, that way you can terminate the game. Alright, so okay, yeah, I am going to explain the rules of the game, right? And here, let me check my notes. Every time I start explaining stuff, I get my notes ready. However, when I actually start it, for some reason, I cannot find my notes. Where are those? Okay, yeah, okay, find it. Okay, the rules of the game. In each turn, right? You go right, left, up, down. Okay, you are here. You go right, you go left, you go up, and you go down. And there are 4 actions, right? Right, left, up, down. Okay, and so there is not a 5th action where you just stay in your location. Just 4 action. If that were to be the case, I mean, the problem would change, right? In a couple of minutes, we are going to calculate some object called value of the states, right? It's like kind of a Lyapunov. There's a kind of a Lyapunov function analogy over there. And anyway, if that were the case, if we had like 5 actions instead of 4, the values would probably change, right? Okay, maybe the policy wouldn't change. Policy, let me just write that down too, right? Maybe I should write the terms in here. This is like the term dictionary. Okay, policy. Right, policy is like, think of it like model predictive control. And what are you calculating? You are calculating, and this is like k1, this is k2, dot dot dot, kn, right? Let's say k10. Okay, and this is like the input. So 0, 10, for example. You calculate that type of input. If you in MPC, model predictive control, okay, I am going to give an example about model predictive control to explain policy. What the term policy here? Okay, and policy is like strategy. And here, recall model predictive control. What are you doing? You are basically solving an optimization problem. And what are you optimizing for? You are, or what is your in that case? What is your decision variable? Your decision variable is here in that case 10 steps, right? U1 dot 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 or U2 dot 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 U10. Okay, you have here in that case 10 decision variables. All right, and you and like using some quadratic cost function, you are minimizing, right? You are tuning these 10 here in that case 10 decision variables, and you are trying to minimize the cost function, and it will be probably the quadratic type of cost function where you try to minimize the states and also the effort that you put in, right? The energy, right? The input, right? For example, you wouldn't probably want something like 10,000, right? An input where you have some okay, you have one type of input and you have like really big input, right? You wouldn't like that type of input is what I'm trying to say. And okay, that was a long explanation. And after you completed the optimization problem, what do you get? You get this. You get the policy. What is that? If you apply this input signal to your plant, I'm going to write system, to your plant, you will achieve or you will have what you desired, right? And what do you desire in control problem? You probably desire some reference tracking, or let's not say that, and you probably desire some state, let's say state, this, wait a sec. Okay, everybody, and what was I talking about? I was talking about what policy is. All right, let me try to explain that a little more. Policy is like strategy, right? Okay. For example, and I was trying to give that unnecessary complicated example of MPC, model predictive control, right? And in that MPC, for example, let's say for three steps, right? You have, okay, you have some input, you have some system, and you have some, let's say directly output or X, okay, and your system is like, for the sake of example, your system is like really simple. This is like this, for example, right? Let's say, and you want to A1 or 1, 1, 2, 3, right? That wasn't over here anyway. 1, 2, 3. Okay, 4. Okay, all right. And this is your input, right? 1, 2, 3. Okay, so you want to find or by using these decision variables, and you will have some cost function, and your cost function is probably going to be like something like right, plus, for the sake of example, like this. Okay, this is your cost function, cost, and how would you minimize that? or what is your tool if you are trying to minimize that? You have decision variables. These are your decision variables, right? Okay, and minimize using u1, u2, and u3, right? Okay, minimize this, and this is your cost, right? And what is your constraint? Your constraint is your dynamical equation. Constraint, or people write minimize by using those decision variables, right? And subject to, it is not such that, it is subject to the constraints. And what are the constraints? Your constraints is of, let me maybe try to do that. Okay. Maybe that's better. Your constraints is this: f of x of k, comma u of k, right? Okay, and this is again for or k 1 dot 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 n. Okay, let me, there is some problem with that, right? 100, or what we said, 3, 1 2 3, or only 3 steps, right? Okay, and what is this? This is your optimization problem. And what is that also? This is modern, the way of designing controllers. Actually, it is not controllers, it is directly the controller signal that you need to apply to the system for your system to behave in a way that you desire, right? And this is called modern predictive control. Okay, and all right, and after that, if you, or when you solve that, what do you get? You get, let's say, you get this, right? For 3 steps, you find your optimal input signal. Of course, this is discrete signal, right? For three steps is this. You find that. Okay. And this is your strategy or policy, right? Okay. So in that grid word example, you have 1 2 3 4 5 6 7 8 9 10 11 12, right? And this is the wall, right? And here, and this is the place that you want to be, and this is the place that you don't want to be, right? And let's say you are here in that location, right? Let me do that, right? You are in that location 9.989. Okay, and what is the optimal strategy? For example, to get the most reward, and for that problem there is only two rewards, right? For being in that location you get +1, and for being in that location you get -1. And also these are the terminal states, right? Okay, and what is the optimal strategy? Probably, just let me get another curve, right? Okay, 1 2 3 4 5, yeah, right? This is the optimal strategy. You can think of it as some type of like an abstract MPC problem, right? There is a connection. Okay, so let's say, I mean, here for that problem we have like right, up, left, and down. We have 4 type of input, right, that we can apply, right? And here for that problem, let's say, and let's name them, right? Let's name them 1, 2, 3, 4. Let's say for you to apply up command, you need to apply 2 volt to the system, right? Let's say, okay, this is vague example, all right? And what do we see? We see, okay, for the first time you need to go up, okay, just 2, all right, okay, and then again up, right, again up, all right, again 2 volts, right? This is the input signal, and this is like the k time iteration index, and all right, you need to go, all right, and you need to do 1 for that, okay, and after that again 1, right, and again 1. So this is, ladies and gentlemen, this is your optimal strategy for getting the best reward. Okay, in MPC, for example, what we were trying to do, we were trying to minimize the cost. However, in value iteration algorithm, or I mean, I don't want to say reinforcement learning directly. However, in that type of games, right, and people say markov decision process, right, in that type of problems, we are not trying to minimize the cost. Actually, we are trying to maximize the reward. And of course, you can say, yeah, it's like kind of the same thing in a way. And yeah, that's correct. But I just want to, make that type of difference, right, clear. And all right. So this is what I was trying to explain about policy. What policy is, right? So let me check my notes. Okay. By the way, I was trying to explain what the rules of the game were, right? And so maybe I should start from scratch, right? About the rules of the game. Okay. Rule 1. In each turn, you can go right, up, left, down. Okay. All right. And therefore, actions. Here's another term that we are required to be aware of, right? Action. Okay. These are the like dictionary. This is the dictionary part that I'm going to write all the terms that are related to this example. All right. And yeah, the grid word for that version, the version of the problem that I'm going to explain has that feature too. All right. If you go right, there is. If you go right, there is. Let's say you want to go right. Okay. And if you go right, there is 0.8 chance of getting there, right? However, there is also 0.1 chance of getting to this location, right? And also 0.1 chance of getting to this location. Okay. And this is not only the case for going right. Okay. And whenever you move, or you try to move in the perpendicular directions, to corresponding perpendicular directions, and in the code I name them as related actions, right? So we have action, for example, going right is action. However, for each action, there are two corresponding related actions. Okay, and here in that case, up and down, right? If you try to go right, you have 0.8 chance of getting there, and also you have 0.1 chance of getting up instead of right, and also getting 0.1 chance of, getting to, wait a sec, you have also 0.1 chance of arriving to the down position. Okay, all right, lower position. And for each action, there are two related actions. Okay, and for action right, we have up and down. Okay, I'm going to, all right, talk about the other actions. And this is for action right. Okay, and also if you, maybe let's read them, right? Also, if you try to go up, right, you have 0.8 chance of getting to this location, and also 0.1 chance of getting to the left of your position, right, where you were, and again 0.1 chance of getting to the right of where you were. Okay, and all right, so this is the case for, again, let me maybe do a little table. Action right and related actions, right? For action right, related actions up and down. Okay, for left, again up and down. Again, let me explain. Let's say you are trying to go to left, and again you have 0.8 chance of getting to that location, and also you have 0.1 chance of getting to that location, and also you have 0.1 chance of getting to that location. 0.8, 0.1, and 0.1. Okay, all right. Okay, come on, just don't make things hard, please. All right, and up, again up, right, and down, left, I'm sorry. Okay, I am going to, like, maybe it's pedagogical or maybe not pedagogical, I'm not sure about that. However, for each DTF, I'm going to explain what I know, right? And I don't know everything, right? However, when I know something, I'm not going to skip over. Okay, so this is like my way of explaining stuff. And all right, you are here and you want to go there up, right? You have 0.8 chance of getting up location, and 0.1 chance of getting right location, and 0.1 chance of getting left location. So this is like the right corresponding unit, and down again right and left action. Okay, when we try to go right, when you press the key right, for example, you have 0.8 chance of actually making the right action, right, and also 0.1 chance of making up action, and also 0.1 chance of making down action. Okay, implementing down action. All right, so this is the case for the other actions, right? For the other actions, and I'm looking at my time as well. All right, So this was the kind of rule that kind of threw me off when I was trying to solve this and understand this problem. And after that, what am I looking at? Yeah, there is the third rule. By the way, I mean the name of or the numbering is not like the conventional. I just number them randomly. So it is not known as the rule number 3 or something. Anyway, so the number 3 and the rule 3, right? Third rule is this. And for example, let's think of it. This map, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And here, this is wall, right? This is wall. Again, if you watch my like BFS breadth first search or direct first search or depth first search YouTube video, right? You know, or you are kind of familiar from that there are some states or there are some locations in a map that you are not able to, reach, okay? And here, for example, let's consider that you are at state 2, all right? And you, you press up button and you actually like 0.8 chance of making the up action, right? And since you cannot go up because it's like the wall, it is the border, right? And you actually end up in this location. So and there are things called transition functions and also reward functions. However, let's not talk about the reward functions yet. However, transition functions, and maybe write them explicitly, transition function, not functions, function, anyway, corresponding to this problem, and is this. You have S, you have action, and you have some S prime. Okay, so let's say you are at state 2, right? And you press the up button, up, right? And you, the chances of you getting to S2 or state 2, right, is, what is that? Is 0.8. All right. Why is that? Okay, let's think of it that way. You have state number 5, right? Let's say you are at S5. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is another map. And there is no wall in that map, okay? And let's say you are at state 5 and you press up and you arrive at press state 2, okay? In that case, state 5, up, and state 2. If you press some action, right? If you implement some action, let's say up, right? Going to the up state, and the chances of you getting there is getting to the upper neighbor of that state is 0.8 for this problem, okay? However, you are at state 5 and you again press up, alright? The chances of you getting to S4, and here this is S4, right? Maybe I should zoom here to that location, right? The chances of you, right? 1, 2, 3, 4, 5, 6. You are here. You are here. This is not a wall. This is like you are here. State at 5, right? And you press up button, right? However, for every action that you are trying to implement, there are two for this problem variated actions, right? Okay, you press up, right? However, there is 0.8 chance of getting to S2. However, 0.1 chance of getting to S4 and 0.1 chance of getting to S6. Okay, and considering that this is transition function, right? Here, this is the first argument is where you are, and the second argument what action you take, right? And the third argument is where you end up, right? Okay, you are at S5 and you press up. The chances of you arriving to state 4 is 0.1, right? Okay, in the same way of thinking, you are at S5, you press up, right? And the chances of you getting to S6 here, right, is 0.1. All right, let's try to focus on this. You are at S5, you press up, right? The chances of you getting to S9 is 0. Okay, and this is the theme that we are going to focus on, right? And this is called transition function, right? And the first argument again is the state where you are, state at which you are located, right? And the second argument is the action you take, and the third argument is where you end up. Okay, and that transition function gives you that. You say, hey, I am here and I do that action, and the chances of me getting to this action, what is that? The transition function answers that question. All right, that's related to what we are going to be doing in a moment, right? All right, yeah. So if you are, for example, these are the walls, right? There are only 9 states, right? Okay. You are at 6. If you try to go, right? Yeah, it's yeah, perfect. Okay, so maybe let me explain that. Okay, I should better explain that. Okay, one sec. Delete again, delete. I am aware of the fact that I am not explaining very clearly. However, step by step we are going to comprehend this. All right, so there for this specific problem, okay, this is like these are the sub examples. Okay, to explain, I am using that sub examples to explain the rules of the game. Okay, also the logic of the Bellman equation. All right, we are building up. Okay, we are slowly building up the foundation. Okay, you are at, there is no war, you are at state 6, right? And you press action, right? Okay, yes. And since there is no right, and since we for the problem we have right, when you press right, you don't go right all the time, right? The chances of you getting right is not 1.0, is not 1.0, is 0.8. Okay, anyway, So state 6, right? And you press right, and the chances of you getting to state 6 is 0.8. Okay, this is the most complicated part, I think. The reason why that is the case is this. You are at 6, state 6, and you actually go right, and you actually go right. You kind of backfires, right? Kind of go and hit the wall, and you again end up at 6, state 6. Okay. In a way, because this is my way of thinking that I use to program the problem, right? And in a way, the right neighbor of state 6, or maybe it would be better for me to write that right neighbor of state 6 is state 6. Okay. And in that analogy, right, in that mentality, right neighbor down neighbor of state 9, here state 9, right, is state 9. Okay. Again, right neighbor of state 9 is state 9. Okay. And you can write the same thing for each one of them. Okay. Each state has right, up, left, and down neighbors. All right. And okay. All right. Now that I am explaining some kind of future stuff, I should get back on track. Okay. So this is our specific problem. Okay. That we are going to solve that problem, right? And why we solve that problem is because if you solve that problem and if you understand clearly, right, you understand the Bellman update or value iteration algorithm, or and also Bellman equation, right? We are going to now see what Bellman equation is, right? And okay, yeah, this is the this Bellman equation, and let me delete some stuff over there. Okay, here, this is the Bellman equation. When you first see that, it is like, what is that? It looks very complicated. However, one by one, right, we are going to decompose it, right, decouple it, and focus on each small atomic particles of that. Okay, all right, each small particles of that equation. All right, for example, we know what max is, right? Like, you have some function and you have some decision variable, let's say for single variable, right? And you are trying to find the max of it. Okay, just okay. So don't get scared about the max, right? Okay. And this is summation, right? We are trying to, let's say we have, I am going to explain S prime, what S prime is now, right now. Okay. S prime is this. S prime is this. For that problem, let's focus on this problem just for once, right? You are here in, it's, let me get another curve. You are here at the state 5. Okay. Okay. And you press up, right? Okay. And I guess it would be better for me to explain the programming aspect and the problem aspect, like simultaneously, right? Because there is a strong overlap, and that will make things easier, I feel like. Okay, because it's kind of, if you are seeing this right now, just right now, right, you are like, it doesn't make any sense. I didn't get anything, right? So because that was the feeling I was having, right, when I was trying to understand that. Anyway, let's try to learn S prime generator. This is the function, all right? S prime generator. All right, this is a function, and let's call it, maybe let's call it capital S E or S prime, right? Let's say, and for that you give me some state S, let's say state 5, and also some action, all right? And I'm going to give you S prime list. Okay, S prime is the, you are at S and you do make some action, right? And you arrive at S prime. S prime is the next state. Okay, you travel from, right? Okay, and for example, and it is better to explain these terms or concepts by means of an example, right? I am a strong believer of explaining stuff using especially small scale examples. Okay, for example, S5, we are at S5 here, S5, and action, the name of the action is, come on, okay, the name of the action is up. Okay, and when you press up, you go, you have 0.8 chance of, we talk about this, right? 0.8 chance of getting to S1, right? And then write the probability as well, right? And also 0.1 chance of getting to left and right. However, there is a catch. There is, maybe there is not a catch actually. If you directly, like the thing we were talking about, right? For example, for this problem, if you can think about that, that would make things easier. What is the left neighbor of S5 is? I am hoping that you are saying S5, state 5 again. Why? Because when you try to go left, you kind of backfire, right? Backfires. You kind of hit the wall, right? And you end up where you were. Okay, because you are trying to move across the wall, right? So if you can consider, if you are kind of more familiar with the object-oriented language, right? S5, let's consider S5 or all of the states as an object, 8 objects, right? And it has, every object has fields, right? And S5 dot left would return S5 because the left neighbor, or maybe you like to be more explicit and say left neighbor, right? Maybe you like to say that S5 dot left neighbor, meaning left neighbor of S5. What is that? It is S5. Okay, again, S, my S looks like 5s. Wait a second, for some reason. S5 dot right neighbor is not S6 because S6 is a wall, right? Again, S5, right? Okay, I feel like we are we get the point, kind of, right? I feel like we get the point. All right. So what I was trying to say is this: for every state and action, there is a corresponding S prime list, right? S prime list. Okay. And for that problem, and S prime list is not all the neighbors, but the neighbors you have a chance of getting there if you take that action. Okay. So again, just one by one, step by step, right? Okay. Maybe let's do that. Let's do that and let's do that. Okay. Here, this is what I call S prime. Here, this is S prime generator. You give me one state and also one action, right? And I'm going to give you the states that you have possibility of getting there. Okay, that's great. You are at S5 location and you press up, right? And I use the word right unnecessary often. I'm sorry for that, and it makes things kind of frustrating. I'm sorry for that. Okay, you are at S5. You press up, and where you have the possibility of getting is first, you go up S1. Okay, and for that up action you have two related action. Okay, and what was the related action of up? Action up. Related actions are, or maybe related action. Maybe this can be a function too. Related action. Generative, maybe, right? You give me one action and I'm going to give you two corresponding related actions. Okay. Is left and right. Okay. Comma. Right. Okay. Related action. Maybe generative. Right? This is the function. Okay. So right and left. Okay. What is the right neighbor of S5? Is again, look at this. Look at this. Again S5. Okay. So what is the left neighbor of S5? Again, look at this. Look at you don't need to think about it if you kind of get the main point and you blindly maybe, or like a robot, right? And you blindly write the things, write your functions. For example, S prime generator function. Write your S prime generator function and then write your related action generator function, right? Okay. And you have 0.1 chance of getting left, and again you have 0.1 chance of getting right. Okay. Up, left, and right. Okay. Okay. All right. Small examples is the like key in understanding these kind of problems. These problems. I mean, first of all, if you understand this problem, first of all, dimension wouldn't matter, right? And you can go like not like 3 by 4, but maybe 1000 by 1000, and also you can go like the 3. This you can consider as like the 2-dimensional, and you can also go, of course, 3-dimensional, 4-dimensional. Of course, it would be really harder compared to these examples. However, if you get the general concept and if you get the, I mean, the general way of thinking or general way of programming to solve the problem, right, to generate the optimal policy, right? And it for you to solve that problem will take longer because programming procedure that would be like tedious. However, after some I mean, okay, I mean, we are going to talk about the programming aspect. However, if you understand this problem and if you try to solve like the three-dimensional or something problem, right? And you need to first of all write the related action function again, right? And that related action function for your three or four-dimensional problem would be much it will take much longer to write that function. Okay, right? You have some related action function, and after that you have some s prime generated function, right? Again, for that four-dimensional case, the s prime, I mean, for you to write s prime generator function, yeah, it will take much longer compared to this case again. However, you have like a couple of functions, couple of subroutines. If you write them, you only need to change you only need to change these like 2, 3 or 5 subroutines for your custom problem, right? And after a while, if you solve that problem and if you maybe get to like 5 by 5 type of problem, right? If you solve that too, and if you build up gradually, you would solve three-dimensional, your maybe 3 by 3 by 3. I mean, that will be tedious. I'm aware of that. However, you can solve that. It's possible. I mean, not like the tedious where you need to think really hard about what you need to program, right? However, I mean, for example, this is like the kind of stuff that you don't need to think extremely hard. You can open up some music, right? While you're coding that, you need to only define these functions, and the definition of these functions, you don't need to really scratch your head. You just okay. First, I am going to name states, right? For example, let's really go overboard and try to talk little about 3 by 3 by 3 type of problem. Okay, in that case, again here, in that case, 1 2 that in that case, and that's like a horrible drawing, by the way. Anyway, you have 3 by 3 by 3, you have 27 states. Okay, and is there another place? Wait a sec. Okay, maybe them. Okay, we are now trying to talk a little about 3 by 3 by 3 problem. Okay, first of all, you have 27 states. Okay, so you are going to name them state 1, state 2, dot dot dot, state 27. Okay, of course you might have some, let's say state 6 is wall, right? You might have that type of features in your problem. And after that, after defining states, and you need to also incorporate your knowledge about the, I don't want to say topology, however, and like the, for example, let's say this is state 1, state 2, state 3, 4, 5, 6, 7, 8, 9, right? Let's say up neighbor of state 5, state 5 dot up is state 2, and state 5 dot left is state 4, right? Dot dot dot, you do that for all the states. And also, since in that case you will probably have like not only up, down, right, left, you also have, right, this action and this action. I don't know what you would call them, and you would probably like to call action 1, action 2, action 3, action 4, and action 5, action 6, right? And you will probably use that type of notation when you try to program your problem. And okay, you need to embed the, I don't know what's the correct word for that. I mean, the knowledge of, I mean, neighborhood knowledge, maybe, right? Knowledge of each state, or yeah, the connection, yes, connection. You need to include your knowledge of connection or variation between the states, right? What do you mean by saying variation? For example, there is a variation between S2, S2 and S5. What is that? S2 is the up neighbor of S5, right? Okay, so maybe you like to your riddle algorithm, or how you would try to go and solve that type of problems, right? First, define your states. I shouldn't, come on. Define the states. Okay. 2, and define the state relations or connections. Okay. And after that, and related action. Construct your related action function. And after that, and I shouldn't talk about that more. Okay. After that, there are some points. There are some things you need to do. However, let's pause for a moment and try to focus more on the problem at hand, right? Okay. And that looks like a mess. Yeah, what I even forget what was I talking about. We were talking about Bellman equation, right? This is the Bellman equation. And okay, so transition function. I feel like I explained what transition function is. However, yeah. Okay, so I explain what transition function is, right? And okay, this is called transition function. Okay, and just let's make a little couple of examples for that transition functions, just to make things more real, right? Okay. Question: t of s1, comma, right, s2. The answer is 0.8. Okay, right. Transition of S1 going S1, S1, right, and S5 is 0.1. Okay, because when you're at the S1 location and you press right, you have 0.8 chance of getting to that. However, you have 0.1 chance of getting to that, and you have also 0.1 chance of getting to the up neighbor of S1. Okay, let's focus on that. Let's focus on that, right? 0.1, by the way. E of S1, again, right action, and S1. What is that? Again, 0.1. Why? When you are in S1 and when you press right action right, you have 0.1 chance of getting to the up neighbor of S1, and up neighbor of S1 is S1. Okay, first you need to define your states. Like when I say define, I mean name them, right? S1, S2, dot dot dot, S12. Maybe you have some walls, and again, for the convenience, like I did, right? You would do something, right? You name them as well, right? Because it would make things easier. However, you wouldn't consider S6 as an state, right? So in that case, you have S1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12. So you don't have S state 6. Okay. And first, name states. Name the states. Second, include your knowledge of, or include your, or define the relations between the states. Okay. Define the relations, or maybe neighborhood. Yeah, that would be better way of saying that. Neighborhood relations. Define the neighborhood relations between states. Okay, so first name them S1 dot 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 S12. All right, that's great. And after that, you do something, and that's the tedious part. Especially, I can even imagine how tedious it would be if you have like 3 by 3 by 3 kind of problem, right? Okay, that would be incredibly tedious. However, you don't need to. It is like tedious, however, not hard. You know what I'm saying? It is not like solving a math problem. It is solving a extremely, maybe first grade math problems type of activity. It will be. All right. Okay. When I say define the neighborhood relations, you literally write something like this. Okay. S1 dot right is S2, because or right neighbor, but I don't want to write right neighbor because it would, it would be longer. However, if you want, you can write that. Okay. And okay, and after that, S1 dot up neighbor. I'm going to write up, however, I'm going to say up neighbor, right? Okay, because I don't want to write too much stuff, right? S1 dot up. What is up neighbor of S1? Again, there is war, that's why, therefore, again S1. All right, S1 dot left is again S1, because there is war in that direction. Okay, that's perfect, right? S1 dot down. What is that? S5. Okay, so what we did for the state S1, we defined the neighborhoods, or neighborhood for S1 by stating each neighbor and also corresponding direction or action that you need to take to reach to that neighbor. and we define the neighborhood variation of state 1. And you need to do this, you need to write explicitly this for each state. And we have actually 11 states. I mean, it says 12, but we don't need to write anything about state 6 because it's wall, right? We don't care about its neighbors or something. Okay. And okay, I mean, because of the way I program the, right? I code the, I generate my code. This is like my algorithm in a way. Okay, maybe you are computer scientist and you are really smart, and probably you wouldn't, maybe you would use smarter way of coding your idea, right? Okay. And again, we did it, we defined the neighborhood variation for S1. You need to do for S2, S3, S4, dot. You need to write these 4 lines of code for each state. Okay. And this part is the tedious part, however, not hard again. Okay. If you have like 1,000 states, I can imagine if you try to use this way of doing things, I can imagine how hard would it be. I mean, you would probably open up some music in the background and you some type of like I mean, I can imagine it would be like a really therapeutic, or right, it would be like your daily session of therapy. Okay, it will kind of relax you, maybe depending on what kind of person you are. Anyway, so transition function transition function is this, right? You are in S1, you go right, the chance of you getting S2 is 0.8. Okay, and we are going to, if you, by the way, if you complete your definition of t, like if you write your t function, transition function, the problem is almost over. Like 99% of your problem is over, just right there. Okay, after that it's like really really easy. Okay, you don't need to do a lot of things, you don't need to write a lot of codes after that, lines of codes after that. Okay, so I'm hoping that you get what transition function is, right? Okay, and maybe I should be like, okay, maybe yeah, we have some space here, we have some space. Okay, I am going to, just for the sake of making examples, right, S1, right, S3, what is that? Or maybe make it in an orderly fashion. S1, what is that? It is 0.1. Why? If you go right, you have 0.1 chance of getting to up neighbor, right? And up neighbor of S1 is S1. Okay, S1, right, and S2. Let's go, one by one, right? S1 and then S2. And okay, what is that? It is 0.8. Okay, transition S1, right, and S3. What is that? It is 0. Okay, S1, right, S4, S4 here, S4 is 0 again. You have no way of getting there. And S1, right, S5, yeah, that's like the only thing that was left to do is 0.1. Okay, and since it's like the total is 0.1, right, you know directly the other ones are 0. S1, S6, S7, 8, 8, 9, 10, 11, 12, or zeros, dot 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 0. Okay. All right. So that was the transition function. And after that, you know what? I'm going to write that is to write maybe to up, right? Up S1. What is that? 0.1. When you go this, you have chance of getting to that part, right? And this is 0.8, 0.8, and this is 0.1, and this is 0.1. Okay. And so the 0.1, right? E S2 up, S2 is 0.8. Why? When you press up, you have 0.8 chance of reaching to up neighbor, and the up neighbor of S2 is S2. Okay, because app is located under a wall. Okay, all right. And what is the other one? E S2 S2 up, S3 is 0.1. Okay, here S3, right? S3. Okay, other ones are zeros. Okay. All right, this is the transition function. And if you program your transition function, 99% of your problem is done over there. Okay. All right. So again, let's remind ourselves what we were doing. We were doing, or explaining actually, trying to understand what Bellman equation is. This is the Bellman equation. Okay. So we, by the way, now we know what S prime is. Okay. S prime is not like all the neighbors, right? Okay. We now know what S prime is. Okay. Yeah, I should talk more about S prime. Like right now. Okay. All right. Okay. This is great. One by one, we are getting there. Okay. So let's say we have S prime generator function S sub p. Let's say. Okay. We have some state and we have some action, and that function will return S prime list or array. Okay. All right, that's perfect. So the best way of understanding this concept is to make some or go through some examples. Okay. And for example, S sub p, this is S prime generator function. Okay. And S1, we are at S1 and we want to go to right. Okay. We press right, and what are the S primes, S prime states? Okay. All right, I'm going to now say that. Okay. When you press right, you go right, and you have S2. Okay. And you also have two related actions. Okay. And these are up and down. And since up neighbor of S1 is again S1, and down neighbor of S1 is S5. Okay, you have this. And also you can also program your S prime list in a way that not only it gives you the S prime states, it also gives you the probability corresponding to each state. Okay, 0.8, 0.1, 0.1. Why 0.8? Because you are here again. I'm going to repeat myself like 100 times. Okay. All right. And S1. Okay, we are in S1 and we go right 0.8 chance of getting to this location. Okay, and also 0.1 chance of getting to one of the weighted action neighbors. Okay, and up. What is up neighbor of S1 is S1. Okay, now or what is down neighbor of S1 is S5. Okay, again these are the polarities corresponding to each S prime state. All right, that's perfect. That's great. That's great. We are building on. Okay. All right. So what I'm trying to say is this. What I'm trying to say is this. I didn't want to just write directly, right? I wanted to build up. Okay. You have rated action, like rated action generator, gen, for example. Give me one action, right? And I'm going to give you two actions. Okay, for example, related action function or generator, right? Okay, right. What is that? It is down and up, right? Okay. Again, related action generator. If you put up as an argument, you would get here up, right, and left, right, and left. All right. Related action generator, right? Down is you are here, you go down, left, right, left, right. Okay. Related action generator. What's left? Oh, yeah, left. Okay, you are here. You are trying to go left and related actions up and down, right? Okay. Up, like the perpendicular kind of actions. Down. Okay. This. I hope you get this. I hope you get the concept of derivative action generator function, right? Or derivative action generator, right? And after that, now we get this over. Okay. So S prime list SP. Maybe write that. Okay, SP. You give me one state and also action, and I'm going to give you S prime list. Okay. So S dot A. Okay. I'm going to write that down and after that explain it. Okay. S dot A and S dot maybe A dot wait a sec. It would be better for me to write related action. Let's say a x action x. Okay. Let's name that related action generator ax, and that function gives us a1 and a2. Okay. All right. Now we know that. Now that we have this, and okay, this is main action and s dot a1. Okay, and s dot a2. Okay. Also we have point 0.8 and point 0.1 and point 0.1. What are those? Those are the probability of getting there. Corresponding probability. Okay? Alright. So so let's let's focus on this part of the problem. Let's use this S prime list generator function or S prime list generator. Okay, S8. Okay, and the action is right. Okay, first of all, AX is right, and if we use the rated action generator for that AX, it would give us up and down, meaning A1 is up, A2 is down. Okay, okay. So just copy let's just copy this. Okay, let's just copy this. Yeah, I am going to literally copy that. Paste, but make it very small. Okay, because we don't have space. All right. No. Wait. Okay. All right. Here. S dot S dot S what dot AX. What is AX? AX is right. X. I'm sorry. S8 S8 and our S is S8 S8 dot right comma S8 dot here up and S8 dot down. Okay, what is S8 dot right? What is right neighbor of S8? Again, it is next to it is left to the wall, right? And that's why S8 dot right is S8. Okay, what is S8 dot up? It is here, S4. What is S8 dot down? It is here, S1. I'm sorry, S12. S12. Okay, that's typo. I mean, really annoying. Anyway, and I was trying to make everything correct. I tried really hard to make any not make any typo. However, yeah, this is life. So, okay, we have S prime and transition functions. It is perfect. Now, 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 we are in a position to talk about the reward function. Okay, I'm going to delete all of them now. I'm going to delete all of them. Okay. Maybe S12. Okay. Okay. So now we know what S prime is. We can generate S prime states by using some function, by coding some function, maybe called appropriately called S prime list generator. Okay, that's my naming convention, by the way. And we know what transition function is. Okay, we see some examples about that, right? And after that, after that, at the end I'm going to talk what value functions are. Okay, and they are not hard at all, so bear with me for a moment. We now see reward. We now see what reward function is. Okay, and reward function is this. You are, people that ask you, or maybe you are the one who is constructing your problem, right? And you, reward function is given in the problem. Basically, what I'm trying to say is that, right? You have some problem, you have some map, and you have some kind of transition functions. And in a way, transition functions are given to you as well. Okay? Alright. However, maybe not explicitly. However, reward functions are 100% given to you, is given to you explicitly. Okay? Alright. So what, let's try. Okay, before that, let me say a couple of words for reward function. Reward function is this. You are in some state. Let's say state 1. And you go to some direction. You press some action. And you go to, let's say, state 2. State 2. Okay. And the reward, you get some reward. Maybe you don't, right? If you don't get any reward, your reward is 0. Okay. This is it. Actually, there's not much to be explained, right? So, reward function is this. You are at some state and you go with some action and you arrive to your arriving position, right? And you get some reward for that. Okay? For example, what did we say for the original problem? We say that S4 and S8 are the terminal states, right? Okay, for example, dying in Mario, when you play Mario, is a terminal state, and maybe you are trying to use some reinforcement learning algorithm, and you define dying as a state, let's say state 100, for example, right? And the reward for that state, reward for being in that state is minus 100 or minus 1, maybe, right? Okay. And for that problem, so what I'm trying to say is this. Since we have the, wait a sec. Since how reward function is written, right? Is this that way, right? Because of its structure, we have state, comma, action, comma, state, right? And for that problem, we have 12 states, and we have 4 actions, and again we have 12 states, right? So we have, right, 48 times 12, right? And it's like 576, right? 576. So if you are determined, you can write. If you're like, no way, I'm not going to use some for or if, programming methods or something, right? And routines and any other programming routine, I am going to write 576 cases, right? And I'm going to define rewards for each of them, right? However, due to the simplicity or due to the structure of the problem, all of those rewards are 0, except this S4 action. It doesn't matter what action is. S8. I'm sorry. S4. This is +1. Okay. And also, and this is, yeah, kind of the starting of a complicated part. S8. This is 8 -1. Okay. What action we take doesn't matter, right? And this is +1 and this is -1. Reward function is the kind of thing that we don't get to use a lot in that problem. Okay, so most of the case the result of a reward function will be, I mean, 0 basically, most like all the time for that problem. Okay, so in that aspect, this problem is not 100% perfect for learning how to code reinforcement learning. However, it is very good for understanding how to, or what, understanding the Bellman equation, right? About understanding the concepts about Bellman equation. Okay. All right. We talk about that. Yeah. After that, the only thing that we haven't explained, I guess, 2 things maybe. The gamma. This is like, like learning rate in neural network, right? Some constant, and this is gamma, and this is called discount factor, right? And for that problem also, it is given to you, directly given to you with the problem. It is not something that you choose, it is given to you. And for that problem, it is 0.9. Okay, right? If you Google, I mean, grid words, you see gamma equals 0.9, right? And also the rules of the game, right? 0.8, 0.1, 0.1, this kind of stuff, you see that as well, right? Okay, and also VS4 is +1, VS8 is -1, right? And value, this is, V means value. This is the value function. Okay, so we are basically trying to find the value of each state. Okay, after that, when we complete the process of determining or computing the values of each state, right? And the problem is solved. Okay, for example, the value function is 0.1 and we started this location, and we just look at which look at our neighbors and which one has greater value. Okay, let's say this is 0.2. This is the value of S5, let's imagine, is 0.2, and the value of S10 is 0.15, let's say. You would choose to go S5. Okay, so your policy or first step is to, if your initial position is state 9, is going upwards, right? Taking the up action. Okay, all right. And again, we are at S5, and we look at our neighbors, and let's say S1 has 0.3 its value, right? The value is point, and we computed the value of S1, and it's, let's say, 0.3, and this is the S1 is the neighbor with highest value, and that's why we go to that location, right? And you just go to your neighbor who has the highest value, okay? And after that you take, it's like gradient descent, but gradient ascent, right? It's like reverse of gradient descent. You just try to maximize your reward, okay? In gradient descent you just minimize the cost, okay? So there is a connection over there, okay? And so we are trying to find these, basically we are trying to find this, and we know what is this is gamma. This count factor is given, right? Is given in the problem, right? And also again, reward function is given in the problem. It's in the problem, it's given, okay? And also transition function explicitly given, and you need to code it, right? However, it is something that we know. Again, reward we know, and discount factor we know, right? And also actions, right? We know what actions we can take, right? And also s prime, we know that, right? And what we need to find is the value function, right? For each state. And the Bellman equation is this. And by using something called value iteration, we just solve this problem. When I say solve this problem, I say determining the value of each state. After you determine the value of each state, the problem is solved. Why? Because let's say you are here, you just after that you go to your neighbor with the highest neighbor. The policy appears directly after you get the values of each state, okay? All right. So okay, let's focus on this. That's, come on. Okay, can be a maybe. Um, anyway, anyway, things not go as you plan. Anyway, in life. So, value iteration algorithm. The algorithm here, first you have 12 states. However, one of them is wall, so you have 11 states. All right. And first of all, in I equals 0, this is an recursive algorithm. Iteratively, we are going to converge to the correct value function, or we are going to compute the values of the states, okay? Real values of the states, okay? And for the first part, for the first task is to just give them 0. Start from 0, okay? You just write 0 0 0 0 0, right? Meaning value of each state. Here value, you have value, and you have also I index and also state, right? This is the value function, right, for this algorithm. And value 0, or maybe you can write here, right? And also state 1, it is 0. State 2 is 0 dot dot dot, right? Okay. And after that let's say you determine, like, I'm going to use 100 iteration, let's say, or 1000 iteration, maybe, right? And for here we can see a for loop, right? For loop. And in each iteration, again, there is another for here. So there is two nested for loops. Okay, one for the iteration index and one for the state. Okay, we are going to iterate over each state here in this location, right? In this stage of the program. And here, since we know when I equals 0 or 1 maybe, right? So I equals 1. I guess there's a, yeah, in MATLAB you don't have, like, you probably, you will start from 1, not 0 is what I'm, in C you will start 0, right? Okay. Okay. So maybe let's write 1. Okay. Alright. And I equals 1. Okay. And after that, since we know what these are, and these are zeros, right? And we know what reward functions, right? And also transition functions. We just use this, and I am going to, for some examples, right? Step by step, we are going to solve this problem. Okay? And we are just going to use this formula, right? This is a formula, right? We are going to use this equation and obtain the next value of the state value, right? Next value of the value function of s. Okay, all right. And this is p, right? Pi, right? This is the policy. This gives you what action to take. Okay, all right. It is going to be clear. Okay, I promise you. All right. So this is the whole code, whole algorithm, right? Sorry, whole algorithm. And I get this from Berkeley, I guess, right? And Pieter Abbeel, I'm not sure what the name. Anyway, I am hoping that I will add the, Berkeley artificial intelligence or maybe advanced robotics lectures, YouTube lectures down in the description. So please check them. And he explained that clearly, right? Okay, okay. All right, now we are going to start. Now we are going to start focus on our specific problem, right? Okay, let's continue. So let me delete them as well, right? Okay, all of them. This S verb is like very annoying. Anyway, I'm angry about this. Okay, so let's, I'm looking at the screen, and yeah, let's focus on this. This is great word problem, right? Here, this is the Bellman equation, value iteration algorithm. Okay, first, what is said? It said in the first iteration, just put zeros, assign zeros to each value. Okay, and we did that, right? That's okay. And in the second iteration, and since S4 is terminal states and its reward is +1, right? And S8 is terminal state and its reward is -1, right? You just assign them directly. And that is kind of confusing part, because we actually we don't use reward functions in a way for that problem. I mean, that's kind of I think the confusion part here in that problem. And since S4 is terminal states and S8 is terminal states, write their rewards directly. In each iteration, you just write 1 for the value of S4 in that corresponding iteration. 1, you just write that. And you just write -1 for the value of S8 in that corresponding iteration. Okay. And so in a way, these two rows are given to you in a way. Okay. So here you can kind of see reward function. However, all of the let's say are si a, right, sj, all of them are zeros. All of I, j, 1, 2, dot dot dot, right? Okay, for that problem. All right. So once again, for that problem, these two columns are, I'm sorry, these two rows and this like 12 times. By the way, 6 is whole, right? And that's why I am going to write 0 for the rest of the iterations, right? As the value of that state. Okay. Because you can't get what I'm coming from, right? It's like it would be much easier to just define states, I mean, name them as state 6, right? Because it's easier to generate a matrix which is like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And then saying, let's say 5 is wolf, and just ignore it, right? However, 1, 2, 3, 4, 5, 6, 7, 8, right? And that generating this type of object, I mean, it would be, yeah, much harder, and there is not a reward for doing that. So I'm just going to go with my, right, go with my way of doing things. Okay, so these two rows and this like 24 numbers are given to you is what I'm saying. Okay, all right, so here is going to be the yeah, first calculation. And maybe not, I shouldn't show you right now. It is going to look complicated, however it is like the easiest thing in the world. Okay, just try to focus on each small computations. Okay, and don't worry, you are not going to do that. I mean, I'm going to do that to explain the algorithm, right? Because the best way of teaching some algorithm or showing how the algorithm works is through some tedious example, right? Okay, so iteration number 3. All right, here we have already these two rows, right, given by us, and in iteration number 3, now we need to find each one of them, right? Each one of them, each one of the entries. And again, here, since S4 and S8 are the terminal states, we just directly write their rewards. Okay, and since 8, I'm sorry, S6 is like wolf, we just write 0, we just ignore it. Okay, write 0. Okay, and after that I am going to tell you this: only S3, only here, only this part will not be 0, other ones will be 0. Okay, you can just take my word for it, I guess, right? And I'm going to show you why that is the case. Okay, first of all, That is the equation. That's the equation. All right. Just look at this table. Okay. This equation is this table, right? Okay. So what I'm trying to say is this. We are here in S3. Okay, maybe just only this part. Otherwise, you might get scared or something. Okay. Let's focus on this part. Okay, just focus on this part. Okay. First of all, what does it say? It says maximize over action. Okay, we have how many actions we have? We have 4. Right, up, left, down. Okay, so let's calculate starting from right. Okay, let's calculate each action, whatever the value of that term is, whatever this term is, and just calculate for each action, and then see what the maximum one is, okay, among them. All right, so let's say, and again, this is the same thing, right? Okay, this equation, I just written this equation. Okay, Bellman equation. Okay, so again, recall transition as action. Okay, what action we are focusing on right now? All right. Okay, so when you see action, right? Okay, just bear with me. All right, this is the action. Okay, and this is the action, main action, and these two are the two related actions. Okay, it is going to make sense. I promise you. Right, you are here in S3, and when you press right, where do you go? You go S4. I mean, just look at the map, right? S4. Okay. Again, by only using the form, we are just using the formula, right? It's very formulaic. Okay. And again, I just copied the Bellman equation. Okay. Again, 0.0 discount factor, it is given to us, right? And after that, just right, I is 2, right? And maybe there is some indexing error, I feel like. Yeah, so we need to do this, I guess. Or maybe I plus 1. I plus 1, yeah. And in that thinking, anyway, all right, just focus, let's focus on this. And this is right, we are here. It is really hard to explain, by the way, I'm sorry. Okay, just one by one. Okay, let's start from scratch. Let's not use that. Let's use for a equals right. Let's just focus on this. Okay, right. In each action, you have main action and 2 related actions. For right, we talk about this. I mean, come on, right? For action right, main action is right, action right, and related actions, action up and action down. Okay, here main action, related action 1, related action 2. Okay, Okay, so you are here, we are calculating for state 3, S3, right? We are here in state 3 and we are focusing on this action, right? What does it mean? What is the right action of state 3 is, I'm sorry, what is the right neighbor of state 3? And that is state 4. Look at the map, okay? So, all right, after you write that, you just copy for the reward function, right? And you also just that argument, and that argument are same. I mean, just look at the equation. Just look at the equation, right? S prime, S prime, S prime, right? Just look at the equation. Okay, we are going to do this together. So I just written, and again, S prime. We are summing over S prime. Okay, and there are 3 S prime states corresponding to each state due to the topology or structure of the problem. Okay, because we are here and when we go right, we can go also up and down. Okay, meaning when you are in state S, the states that you are able to travel by some action is these states are called S prime states or the next states in a way. Okay, and since when we try to go right, when we try to go some action, do some action, we also there's a chance of us getting to, I mean, making 2 related actions and 1 made action and 2 related actions. Okay, and number is number 3. So there are 3 S prime states is what I'm trying to say. Okay, I am strongly hoping that you kind of get what I'm saying. Okay, I know I am a terrible explainer of things. Okay, for every action, I mean, maybe you you just don't need to think about it. You just use this formula, right? You use this equation like blindly. Okay, for each action, for this action, you have 1 main action and 2 related actions. Let's call it related action 1, related action 2. Okay, all right. So S3, you are here. This is your state. This is where you are, right? This is here. We are here. We are focused on S3. Okay, and when I say A, I could have written just this. However, that would look really complicated, so that's why I didn't write that way. Okay, I could have written that way. So here A in that location signifies action right, and here the action in that location signifies action up, and here action down. Okay, so that's the correct way of thinking to get this. Okay, here we are here in that state. Again, there are 1 main and 2 related actions. Okay, and you can think of it this state as S3 dot right. And what is that? or what does it mean? It means what is the right neighbor of S3 is, and the answer is S4. Okay. And what is the here up neighbor of S3 is S3 again, right? Because there is a wall. All right. Again, what is the down neighbor of S3? It is S7, right? Okay. And when you kind of write this, the structure of reward function also appears directly. You just can copy that, because look at this. The way the arguments are ordered, it's like the same. Okay. So when you write them, you basically get the structure of reward as well directly. Okay. And again, rewards were given to you in the problem explicitly, even, right? Okay. And after that, you directly blindly use the formulae, right, at hand. And what is S prime here? S prime, I'm sorry, let's clean up this a bit, right? What is the S prime? Let's not focus on here. S prime 1 is S4. S prime 2 is S3. S prime 3 is S7. Meaning S prime generator for S3, and the correspond and the action is right. When the action is right action right, it is going to give us in this order: S4 the main action, the states where you end up. If you take the main action, for every action we have a main action and two related actions. Okay. And after that you have S3 here, S3 and S7, and the chances of you getting to those S prime locations or S prime states is in that again, okay, 0.8, 0.1 and 0.1 in that order. Okay. Main action, related action 1 and related action 2. Okay. By the way, main action, related action, state prime list generator, and related action generator these are my terms. These are my terminology that I use for creating the program that I'm going to show you, by the way. Okay. So what I'm trying to say is that you write that again. We are going to maximize our actions. How many actions we can take? 4. Action 1, 2, 3, 4. Right, up, left, down. Okay. This was, what was that? This was action right. Okay. So we have 4 of them, right? Okay. But let's focus on this one. Okay. So let's just, since we have that, I'm sorry, since we have this term, let's write write their values, right? Okay. And what is that? Again, we've been over this. This is transition function, and by using the structure of the by using the topology of the map and also the problem statement, we know what that term is, right? Action here, let's make this like that. Okay. Action, this is the main action, and 0.8. This is 0.8. Okay. And rewards, all of them 0. Okay. Just take my word for it, or just, yeah. And here discount factor. And here, what is that? We just written that by using the table. Here, just look at the table. I2S4. I2S4. And what is that? This is this one, right? Okay. And what I'm trying to say is that every term we have what those terms are. Just write down their values and compute them. Okay. All right. Here, because I mean I'm getting really tired, and also I didn't think it would take me this long to explain that. Anyway, I'm a slow explainer, I'm sorry. Okay, there are four actions: right action, up action, left action, and down action. Okay, each one of them, we just computed these values. Okay, and we have four numbers. However, what do we need? We need to compute the maximum of them, right? We need to compute the maximum of them. Okay, what is the maximum of among those numbers? Is 0.72, right? Okay, so 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 we just computed we just computed v3 is 3.72. Okay, congratulations, you just computed this entry. And considering we will have like 100 iterations, and we have like, I mean, where states, but one of them is wall and two of them are terminal states, and that's why we can consider like we have effectively in effect 9 states and 100 iterations and 900 we need to, and that's like the critical part, I guess, or funny part. We need to do this for 900 times. We need to do something like this for 900 times. Okay, and by the way, this var, if you choose your iteration number, maximum iteration number to be as 100, I mean, you can choose 1000, right? And in that case, you would do that type of computation for 9000 times. Okay. All right. We computed this. This term is what term this term is, right? Okay. 0.72. Okay. So please take my word for it. Other ones are zeros. Okay. The other ones, let me write them. 0.72, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Take my word for it. Okay. I mean, you can do that. You can do and see, yeah, it's like 0, 0, 0, 0. And what's the maximum of those terms? Again, 0. You would end up with that. And since I am showing you by manually doing that, I don't want to do that all of them, right? And I am going to do a couple of them, and couple of them that matters, right? And after that, we are going to focus on how we can program that in MATLAB. Okay, MATLAB. Let me just write that. MATLAB, not Python. MATLAB. Okay. Okay. Let's focus on when I equals 4. Okay. Here, 0.72, right? Okay. So again, take my word for it. Only things that matter is S2, S3, and S7. Look at the map just, okay? Because I'm getting really tired, by the way. Okay, that's why I'm yeah. Okay. Here. S equals 2, right? You just blindly blindly write this. You don't need to think about that. You just write this. And to make things even easier, you will have your own subroutines coded, right? Okay, for example, again, s prime list generator is the type of function. Okay, and also action. What was the name of that function that I was talking about? Related action generator. Yeah. Okay. Okay. So here there are 4 actions, and let's look at each one of them. The first action, right? The main action is right. Related action 1 is up. Related action is down. Okay. Here you are here, and you take right action. And what's the right neighbor of this? S S3. Okay. Alright, and when you have that, you have the structure of reward as well because of the structure of the equation. Okay, and after again, just by using by we have s prime. S prime is s prime 1, or the first entry of first element of s prime list. S prime is 2, and right action right is s3 s2 s2, and you are like, how come s2 appeared like 2 times? Because s2's up state s2, the up neighbor of state s2, sorry, up neighbor of state s2 is again s2 because it's under a wall, right? Located under a wall. All right, and again down neighbor of state 2 is state 2. Why? Because there is a wall underneath the state 2. Okay. Okay. So, and here this is s prime and this is s prime. Those two terms, they might be same. Okay. Okay. So you know what transition function is. We talk about that, right? And you know what reward function is. We again talk about that. And after that, and since you use only the table, this tables, use these tables to look up the values for the value functions, right? You just write them, right? And you just compute them, okay? And we just computed for action, right? And after that, for the action up, here we computed. Action left, here we computed, right? Here action down, here again we computed. And what is the maximum of those 4 numbers? And is this number, right? Okay. So what we have found, it is like really long, since these are like long kind of procedures or something, or they may appear to be, right? We may forget what we were even doing about, right? And computing, we just solved v v v4 s3. We just solved this. Okay, this is like again I minus 1, right? I4 equals 4 here. Okay, and again another state that matters, the value of it is not 0, is s3. Okay, this is like the most boring video, by the way. Anyway, again s3, 4 actions. We have 4 actions. Each action we have main action and 2 related action. 1 main action and 2 related action. Okay, dot. And here we are our S is S3 and action, right action, okay. What is the right neighbor of S3? S4. Okay, what is the up neighbor of S3? Again, S3. Okay, just directly, you don't, if you have the function, you don't need to think about that. Okay, function does that for you, right? The subroutine that you coded, right? What is the down neighbor of S3? S7. Okay, and since you have that structure, reward functions have the same structure, right? Just look at the equation again, right? And just write these are S primes, right? S primes, S prime, S3, action is right, is in that order, right? S4, S3, S7. If you don't get this, just go backwards or go at the beginning of the video, right? And try to understand what S prime states mean, right? They don't just mean the neighbor states of the state that we are focusing on. These specific neighbors, okay? And it's like counterintuitive. You don't expect for S1 to be the neighbor of S1 in a way, right? Just don't think about the S primes as the neighbors. It is kind of special neighbors, okay? Because to determine what the neighbors are, you need to only specify your location state. However, these S prime states are different kind of neighbors, special neighbors. You not only need to specify the state that you're in, you also need to specify the action, right? Okay. Okay. So after all, you compute by looking at the tables, the values of the values, right? Look at the table and write them down, right? And compute them just blindly. Okay. The reason why I show this in a lengthy way, I mean it took a little long for me to get that. Okay. Again for S7. S7, okay. Here 4 actions, and each action we have main action and 2 derivative actions. Okay, here we are S7, right action, right neighbor of S7 is S8, again the same structure, again discount factor, and Vi of S prime is S8, right? And the same way of thinking goes for the other cases as well, right? And after that, you just write the values of each term by looking at your functions, by using your functions, subroutines, and also the tables. Okay. And again, we found those 4 numbers and we get the maximum of that 4 numbers, right? And after that, what we have found? We have found is S minus 1, right? We found S4 of S7, and what is that? Is 0.4258. I'm sorry, not 58, it's like 84. 0.4284, okay. And we put that number in the table that we are constructing, right? Okay, here this is our table. Okay. Yeah, after, okay, it's over. And after that you do the same thing for 100 iteration or maybe 1000 iteration, right? And that's why of course you realize that you need to use computer for that. And I am going to show my MATLAB program. I already programmed because it would be impossible. Even, I mean, it will be impossible for me to explain it and write it at the same time, right? First, I'm not a programmer, right? I'm an electrical engineer, control engineer, and second, because I mean I don't have that. Some other people have that ability. They can speak on the phone. They can talk. They can listen to music, and they can write a very complex code. Computer sciences they exist for that reason. Okay, and however, I'm not one of them. So I written my code beforehand, and I'm going to show you, especially the critical parts, right? However, it is there are some couple of MATLAB specific related issues that I need to talk about, right? And that's all. Okay. In the next video, we are going to look at the MATLAB codes. Yeah. Okay. And also we will see some subroutines, for example, S-prime list generator, right? And related action generator, right? And okay. Thanks for watching.